As we turn to the next phase of the synthesis of cholesterol, we have created a very long hydrophobic chain that is 30 carbons long. And in the 30 carbons, there are lots of single bonds which we can rotate. There are quite a number of double bonds which have no rotation. And so when squalene binds into the enzyme, we start to see the working of where the rings actually start to form. And so we have 3 6-membered rings and 1 5-membered ring. The first reaction that was important is to create an epoxide. Tell me something about an epoxide that you know or that you can see. What's important about an epoxide? Is the epoxide stable? Not at all. The epoxide is very unstable. Actually, the Department of Energy and the DoD are really interested in epoxides because they make wonderful explosives. Okay, we are also concerned about epoxides because epoxides can form in several of the chemicals we have in storage, and unfortunately they love to be formed right around the ring of where the cap is, and they can be explosive. And so any epoxide formers, you actually have to watch out, and they can't be left in labs too long because of the danger of them exploding in your hand when you start to use them. Okay, so very unstable. And as you can see, with this slide has already previewed what's going to happen. Okay, what's going to, oh, good night, have mercy. Stop. What's going to happen is a concerted ring closure where it's 1 to make that ring, 2 to make that ring, 3 to make that ring, 4 to make that ring, and this to make the hydroxide. And we create the ring structure. Now the animation said it takes 23 reactions to get to where we want, okay, to get to this. So I won't show all of the ring movements because that is not necessarily important. Okay, but we're on the road to get to cholesterol. All right. Now we're going to get to cholesterol after a couple more steps. Okay, that's all you need to know. Okay. It's a lot of movement, but really what we're doing is you can see that we change where the double bond is. Okay. We also move around or lose 3 methyl groups. And so this methyl here lost, and both of these methyls there lost. And we have cholesterol. Okay. The numerical numbering of these seems pretty logical as you go through the ring. 1 through 5, 6 through 7, 8, 9, 10. Okay, now I got myself into trouble. 11, 12, 13, 14, 15, 16, 17. Okay, and then we go 18, have no idea why. 20, and then 21, and then through the ring structure, through the, alkyl structure. Now, you don't need to memorize this because you can always look it up, but there is a systematic way to number the cholesterol. All right, we can make cholesterol, and we do that in the liver primarily if we need them. Unfortunately, the American diet doesn't necessarily need to make cholesterol very often. Okay? Most of the time, we get enough cholesterol from our diet. Now, cholesterols are very hydrophobic. Oh, wait a minute. And we eat them. Now, is this right here bad cholesterol or good cholesterol? Right? People are concerned about, do you have bad cholesterol? Do you have good cholesterol? We use that terminology all the time. Even in the doctor's office, we use that terminology. Is that the good cholesterol structure or is that the bad cholesterol structure? Good. That is correct. It is good. And it is also bad. Okay? Cholesterol is cholesterol. Unfortunately, we use the nomenclature in our vernacular in a very bad way in terms of describing. The structure of cholesterol is both good and bad. It just depends on how much you have of it. But the cholesterol that is in your bloodstream really has very little to do with just cholesterol itself because it's a totally different particle. Because it is so hydrophobic, what we have to do is carry the cholesterol inside a vesicle. Okay? So cholesterol can be inside the middle, surrounded by a lipid membrane. There are some cholesterol in the membrane itself, and there are proteins embedded in that particle. Now, there are several particles that are found in the bloodstream. And so we have chylomicrons, the VLDLs, the LDLs, and the HDLs. All right? And so inside of that particle are fats, free cholesterols, cholesterol esters, and proteins. All of those will bundle together to create those 4 entities. Okay? One of these is considered good. One of these is considered bad. Good, bad. The other 2 aren't even described. When you make a blood concentration measurement of cholesterol, which happens every time you go into the doctor's office, you're measuring the concentration of those 2 particles. Okay? The amount that you have usually is a number that's 200, okay, per deciliter, and I believe the numerical value is 200. Anything under that is considered relatively good. But you can have less than 200, the numerical value, and still have bad cholesterol because there is a ratio between these 2. And so you might have an overall concentration that is good, but you may have too high LDLs and too low HDLs even in that numerical value. If you take a look at the 4 pictures, you see the chylomicrons are huge, the VLDLs are larger, we get smaller and we get smaller. As we go down, what we are talking about is very low density lipoproteins. We have low density lipoproteins and we have high density lipoproteins. The size is not what's important in terms of what is healthy or not healthy. What it is the concentrations of everything inside. The chylomicrons are the first things that are formed from the gut itself and transported to the liver. If you take a look at that, we can look at the densities themselves and we can see that we've got different density values. Okay, but what's really important are the percentages. Protein, phospholipids, this is then the membrane that's surrounding, and what's inside usually are free cholesterols, cholesterol esters, and fats. Normally we're bringing in lots and lots of fats, not a lot of cholesterol. If we go even to the VLDLs, okay, proteins and phospholipids, and then look, 7 and 12, so we got about 19% cholesterol. Here we had 4 total, and about 50 fat. In the LDL, what we see is lots of protein, lots of phospholipids, but look, 8% free cholesterol and 37% cholesterol esters, so that is 45. 45% of that particle is cholesterol. 10% is fat. The HDL goes down to a total of 17% cholesterol. So the one particle that has a lot of cholesterol in it is the LDL. All right? And so this has the ability to be very, very sticky. And it's sticky when it goes into your veins and arteries. And so by chance, if the particle hits the side and breaks apart, that material doesn't get dissolved in the blood. It can plaque against the arteries and veins and can create a blockage. having too much LDL is indicative of disease. Now, what really happens is this. You go to Taco Bell, okay, and you are eating lots and lots of fat, lots of cholesterol. I'm not exactly sure how much protein, but, you know, they make an argument. All right, and it gets broken down, it gets repackaged, and the first package is this very large particle called a chylomicron. That tends to go into the circulatory system, and it heads to the liver. Now, those can deliver free fats and free cholesterol to tissues, but it's not very efficient. Most of the fats and cholesterols head back to the liver. All right, the liver repackages everything, all right, and what it will do is it will send out VLDLs, all right, and those are intended to go to all of the tissues outside the liver and to give fat and cholesterol back to the tissue, everything around. And all of these will, the different proteins on the surface of the VLDLs will bind to the tissues and will internalize those particles, and will take some of the fats and the cholesterol out unless your tissues are saturated. If they are saturated, as some of the particles are taken out, what we do is we end up with LDL. It still has lots of cholesterol, lots of fat in it. If your cells needed the fats and cholesterols, we hope to be sending back HDLs. And so you have this efficient repackaging into the liver. We send out the fats and the cholesterols. The tissues absorb them because you've been working out and you need to replenish them. And then we send back HDL. That's what we want to have happen. Unfortunately, we send all these particles out, and what happens is the LDL concentration becomes very high, much higher than it should be. And having the LDL particle in the blood system for very long periods of time tend to create plaques. Okay? How do we lower LDLs? Okay? What are treatments to lower LDL? Most of the time, the first strategy is to change your diet. Eat better. Less processed foods. Okay? Less processed foods tend to have less cholesterol. All right. Unfortunately, there are people who have wonderful diets, who exercise all the time. Okay, change your diet and exercise. That they always tell you those two things. All right. But people are very fit. They don't eat a lot of processed foods, and they still have high LDLs. There are some genetics that will make the synthesis of cholesterol even in the absence of the body telling that you need it. And so there's a whole class of drugs called statins that will prevent the committed step to mevalonate. It inhibits that particular enzyme. And so there could be, you have a wonderful diet, and you have a perfect amount of exercise, but your body is always making cholesterol. That's when we start, that's when the prescription of the statins come in. Statins are one of the most profitable and most often prescribed drugs to the American public, because lots of people are having cholesterol, higher cholesterol than what we would want. All right, so here is the static picture of the animation. And what happens is, if a cell needs material, it will send the receptors out to the surface. If the cell has plenty of cholesterol, fats, and material, it will not send the receptors out. And so if the receptor is not on the surface, the LDL particle will pass, and that's how we can have way too much LDL in our bloodstream, because every cell it encounters has way too much already. Now, how do we normally think about regulating the synthesis? We have talked about a little bit about this before, but remember, insulin is going to enhance the committed step. Glucagon will inhibit the committed step. Cholesterol itself, okay, will come back and do a feedback inhibition. Cholesterol will also, if it is high in the cell, stop the receptor from being on the cell surface, and so it stops endocytosis on the inside of the cell. And cholesterol itself will then start to make esters of the cholesterol for storage. And so cholesterol itself that has the hydroxide can be incorporated in membranes. Once we have the esters, it will not. Now, in the liver, the esters are repackaged on the inside of the particles. When we start making derivatives of cholesterol, we start making a whole different type of molecule that can be useful for digestion and for a whole set of hormones. The first set of derivatives that are produced from cholesterol is really the beginning part of the degradation of cholesterol. And so what we're going to do is we're going to make the cholesterol a lot more soluble. And so we will use an enzyme called cytochrome P450 using molecular oxygen, and we'll add lots and lots of hydroxides. We'll also add a very polar molecule, either glycine or another charged molecule, to the end of the chain. And what we do is we get a molecule that has both polar and nonpolar regions, and they can be used as what are called biosalts, which then can dissolve fatty material in the stomach so that they can be solubilized and digested. The bile is stored in the gallbladder. Cytochrome P450 is an interesting molecule itself. It catalyzes hydrations of simply a methyl group to a hydroxide using molecular oxygen. It also needs NADPH. One thing about the reactions here, it is used for cholesterol. It binds to very hydrophobic molecules. It's intended for cholesterol, but it will hydroxylate any organic molecule that is very hydrophobic and place hydroxides on it. What it is tending to do is trying to make it soluble so that it can be excreted out. One of its targets that cytochrome P450 works on, other than cholesterol, is drugs. Many drugs are hydrophobic based, and so cytochrome P450 is one of the enzymes that will clear a drug. Every time you give a drug, there are some concentrations that you are concerned about and lifetimes. And so to get a therapeutic response, you have to give enough drug that the concentration goes high enough to bind to wherever you want to bind, whether that be an enzyme or whether that be a receptor. And so the dosages you take are based upon your weight and how large you are. Usually they determine that by age. Okay, and so you take 1 pill a day, 2 pills a day, 3 pills a day, or whatever the dosage is that they calculate. The other thing is a half-time or a lifetime that the drug will be active in the system. There are many enzymes that the drugs will, as they go through the bloodstream, react with. Cytochrome P450 is one of them. Most of the time, the drugs that we take now have been identified very closely in it binds specifically to the receptor or to the enzyme that we want to function for. But we still have side effects. Many of the drugs that we used to do, we would throw drugs at people and they would bind all sorts of things and cause side effects. Now we can develop drugs that actually bind really tightly to the one thing that we want. A lot of side effects come not from the drug itself, but from the derivatives of what actually happens when they're being broken down. Cytochrome 50 is, P450 is one of those that when you go through drug trials, they will treat the drug to cytochrome P450 to see the outcomes, what are the degradative pieces of that, and then they will test to see if those are those have side effects or are toxic. And so there are a couple other enzymes that they treat the drugs to see what kind of breakdown products there will be. And so cytochrome P450 will detox any foreign substance and sometimes make the detoxed items a little bit more reactive. If we change to the hormones, we are still hydroxylating, and we hydroxylate the 20 and 22nd position to get a dihydroxide, and then we break off the tail, that hydrophobic tail. Pregnenolone is the precursor to all of the steroid-based hormones. And so whatever hormone you have that is steroid-based, it comes from this particular structure, shortened. And all the hormones are derivatives, usually smaller in size than cholesterol and a lot more hydrophobic, a lot more polar entities added to it. And so there are different classes of them. The two most famous are the testosterone and estrogen, which are the two smallest of the hormone classes. When you go back and look at the synthetic pathway, okay, that 5-membered intermediate that was the step away from mevalonate, the isopentenyl pyrophosphate, is very important in the synthetic processes of hydrophobic intermediates. And so we have the quinones, okay, we can synthesize. We can also, see that this is used in plants quite often, where we have chlorophyll, rubber, all the vitamins that are derived, vitamin D, the beta carotene, and so a lot of structures that we use are based upon this particular key intermediate. And so if you think about key intermediates and metabolism, there are some that come up and are seen quite often. Pyruvate, biggie. Acetyl-CoA is huge in our bodies in the synthesis of a lot of different things. This one plays a very big role in lots of synthetic pathways. And so this is one of those biggie in terms of structures that are used all over metabolism. Now, we have synthesized sugars way before we have synthesized fats, and now we're going to talk about the synthesis of the nitrogen compounds, particularly the amino acids, and then a couple other important nitrogen compounds, including the nucleotides that are found. When we look at the synthesis of nitrogen compounds, the first thing that we really need to get is nitrogen itself. Atmospheric nitrogen is the largest source of nitrogen, although atmospheric nitrogen is very unreactive. If you think about the not the three-dimensional structure, but the electron structure of a nitrogen, it's a triple bond. That is hugely energetic to break. And so you've got really two ways to break down nitrogen in the natural process. One is lightning. If you are in Georgia watching a golfing game, the golfing tournament this weekend, you are a little bit too close to the lightning. Did you see that on the news? Man, I saw it hit that tree and it started raining, so everybody went under a tree. Never go under a tree during a thunderstorm. It was a bad move. But the electricity involved in a lightning strike can actually react with the nitrogen to create the nitrates and nitrites, and it can come down as nitric acid. Now, that's not how most nitrogen is fixed into the biological system, although that is one method. We can't do it, okay? Plants can't do it, animals can't do it, but little tiny organisms on the roots of plants can actually react with the nitrogen and what's called fix it or break the triple bond to create ammonia that can be incorporated into synthetic pathways. We can do this industrially with nitrogen and hydrogen under what's called the Haber process. It's really intense. You have to use a lot of pressure to get that done. And a lot of our fertilizers that we use this process to create nitrogen. And so we will enhance soil with this organic nitrogen from that particular source. But the majority is done in the microorganisms in the roots. We're going to use an enzyme called a nitrogenase. To break it with enzymes to take nitrogen and produce ammonia, we would need 6 electrons and 6 protons to make ammonia, although there's a side reaction that also makes hydrogen. So the overall process is 8 electrons and 16 ATPs. So if you think about the nitrogen in that triple bond, 16 ATPs is a lot of energy, plus the energy of the electrons. If you think about that, 2 electrons, when we carried it as NADH, made a whole bunch of ATPs. And so this is a very energetic process. The first enzyme in this is a reductase. And what we actually have is a iron sulfur center that can hold a lot of electrons. Also contains an ADP-ATP binding site. And what the electrons or the ATP does is to change the conformation to allow the electrons to be accepted and then donated into the next enzyme. The electrons actually come from ferredoxin. Where was ferredoxin found? Is it in photosynthesis system 1 or 2? Does that help? Could be 2. It's 1. Okay? And so photosynthesis, really fast. Light comes in. It excites photosystem 2. Electrons start flowing. The water reacts with manganese center to take electrons out, gives it to the tyrosine molecule. The tyrosine molecule gives it to the P680 in photosystem 2. So I go through all the channels in photosystem 2. I give it to Q. Q goes to cytochrome BF complex. Protons are pumped across, and electrons are given to plastocyanin. Plastocyanin goes to photosystem 1. Light shines. What wavelength excites photosystem 1? Yeah, P700. Electrons flow through that. It goes to the ferredoxin, and the ferredoxin is supposed to go to the NADPH reductase to give the electron so that NADP plus can pick up the H, the hydride, and create the NADPH reductive. But what happens when I run out of NADP plus? Where do the ferredoxin electrons go? It can go back to the cytochrome PF complex. That's one pathway, and that can make a little bit more proton gradient to make more ATP. Also, the ferredoxin goes and it upregulates several enzymes in the regeneration pathway for carbon fixation. Okay, and so it has to reduce those enzymes to make them functional. Now we know that ferredoxin can go all the way down to the roots, translate, and give the electrons to break down nitrogen. So ultimately, the electrons are coming from photosynthesis or the sun. So this is where all of those electrons come from. The nitrogenase actually has a cluster that holds onto the electrons for just a little bit to be able to transfer over to the iron molybdenum cofactor, and which the nitrogen actually is having the reactions with the electrons and the hydrogens at that particular place. So we have a P cluster and an M cluster. the M cluster actually is kind of interesting, okay? If you look at this side, this comes up towards us. This is a sulfur here, and this is the iron in the iron. So from this side, the iron is up. From the back side, it's kind of open. So this is that same cluster flipped over. And this iron, that iron, that iron, this iron, that iron, and that iron make, well, actually, this iron and this iron, that one and that one, are all involved in coordinating the nitrogen that sits. That sulfur that is now down below is the one that's sitting up here in that structure. So the nitrogen fits down wonderfully. How many electrons does nitrogen have to absorb to get to the ammonia? Go back a few slides. Not the overall process, not the one with the side reaction, but directly. 6. 1, 2, 3, 4, 5, 6 irons. Every one of those irons is going to donate an electron to the nitrogens. As they donate in a stepwise fashion, it will pick up protons on the way. And so electrons will be donated, protons will be picked up, and you will eventually break that particular bond. And it comes off as ammonia, and as soon as it gets into the solution, because of the pKa of ammonia and the pH of the buffering system, it will become the ammonium ion. What did we learn in the degradation of protein about ammonium? Is that good for us? It's poisonous. Okay? Even at 60 micromolar, it becomes poisonous. And so we did learn one particular example of an enzyme. In degradation, it was focused this direction, in that we will create an intermediate and we will have the nitrogen fall off. But in the synthesis, we will do the reversed reaction and we will create glutamate. All right. This right here was a particular structure that we needed to know the name of. Do you remember what the name of that particular structure is? It's a functional group. We called it, it's not exactly, we called it something different in biochem because it's used quite often. It is reversible. We can add water across that. Schiff's base. And so the Schiff's base is used a lot within biological systems, and you should be familiar with that particular intermediate. Okay. Interestingly enough, we said that reductions, and that's what's going to need to happen in the synthesis here. We have to reduce that. We're going to use NADPH almost all the time, although this particular enzyme can survive by using NADH. And we usually use NAD plus as the accepting. All right. Interestingly enough, when you attack this, NADPH, and if you use this, you're going to attack at the carbonyl. Even though there is a positive charge on the nitrogen, you will actually have the hydride attack because the intermediate that is temporary is a neutral nitrogen. And then because of the pKa, you can pick up the proton. I would write it as a movement there. So this is 1, 2. You could write that. That's perfectly fine. Or you can write that movement. That is saying the same thing. Now, the dehydrogenase is the reason why we only synthesize the L version of the amino acids. And so if you go back to the Miller experiment where they synthesized amino acids using the what was determined to be the primordial atmosphere and used electricity to simulate the lightning strikes, the synthesis of amino acids actually happened, but they actually made them in a racemic mixture. And what we find in the human body is only the L versions of the amino acids. The reason why we have the L version is because all of the amino acids are synthesized with the dehydrogenase. And so on one face of the substrate, the amino acid binds, and here is the protein. The protein aligns the hydride that's going to attack, okay, and it only attacks one face. And so when we have the ability to attack something that is flat, okay, we can attack either side in an organic flask, but because the enzyme forces the binding and the positioning between the two entities, we will only get one stereogenic outcome, and all of the amino acids are L. All right, amino acid synthesis overview. Oh my goodness gracious. There is a lot of synthesis going on here. Okay, what you need to know from this is which amino acid fits into the starting point of a pathway. And so this group right here comes from oxaloacetate. Okay. This group over here comes from alpha-ketoglutarate. Provate will make these 4. 3-phosphoglycerate, make those 3. The erythrose 4-phosphate can help make tryptophan. Phosphoenol provate will also be involved in phenylalanine, tyrosine, and tryptophan. And glucose 6-phosphate will go for histidine. All right. Name what pathway, what pathway is this molecule in? Glucose 6-phosphate. What pathway are we in? Glycolysis, half right. What's the other half? Not citric acid cycle? Gluconeogenesis. Okay, so we can go either direction. 3-phosphoglycerate, what pathway? Glycolysis or gluconeogenesis. Erythrose 4-phosphate, what pathway? Pentose phosphate pathway. Provate, okay, that one's glycolysis, right? Gluconeogenesis also. Then oxaloacetate from the citric acid cycle, alpha-ketoglutarate from the citric acid cycle. If you went through Biochem 2, you learned these associations in the degradation. The synthesis is no different where they come in and out. Okay? And so hopefully this is not relearning that entire scheme. All right? And so let's start and do one of the most simple synthesis in the pathway. Now, you have learned how to synthesize one amino acid at this moment in time. Which one? We have seen the synthesis of one amino acid. Did it go by you? Went right by you. We know how to synthesize glutamate. Alpha-ketoglutarate plus the ammonium. Okay, so you've got 1 of 19. Here's number 2. All right, we're going to do glutamine. What we're going to do is we're going to add an amine to the R chain. All right, when you look at an enzyme reaction, okay, and so this could conceivably be a exam question. All right, we're going to synthesize this glutamate, and this intermediate. Okay, I'm going to give you one step in a process. All right, so this reacts with ATP. ADP is the leaving group, and I have this phosphorylated intermediate at the end. What in the world do you start doing? What's a strategy by which you approach these? Okay. Base. A lot of the times a base is involved, and you also have an acid, because you always have an acid and a base in a biological system in the enzyme. So you might start writing a base down and throwing electrons around, throwing arrows. I would do one thing before I start just drawing arrows. Okay? First thing I like to do is do some inventory between the beginning and the end to find out what changed. So I look over here. If I look at the reactant and I look at the product, any changes around here? Nope. Changes around here? Nope. It changes around here? Nope. Changes around here? Yes. Okay. Did I change anything here and anything there? Let's see. What in the world's different? Okay, so this oxygen is bound to that carbon, right? This oxygen is still bound to that carbon, but what do I see? Double bond. Where do you see the double bond here? It's doing what? It's in resonance. So to facilitate the end, I'm going to stop the resonance. I'm going to say, okay, if that is a double bond, then I must have a negative charge here. Okay? And then what we see is this oxygen is right there, and that's got something different happening to it, right? It's got a phosphate attached to it. All right. So I know something's going to happen here. All right. ATP. ADP. Does that tell me anything? What does it tell me? It's going to attack a gamma phosphate. Okay? You can tell where the ATP is attacked by what is the leaving group. Is it ADP? Is it AMP? Is it PP? Or is it inorganic phosphate, the two PIs, and the diphosphate coming off? And so because I see one phosphate, I know I'm going to attack the gamma. And I don't need a base. Why? I already have a nucleophile, right? A negatively charged intermediate. We'll attack at the gamma. Every time I attack the phosphate, what do I have to do? Because I have a pi bond, the intermediate always has to be a full charge on one of the atoms temporarily. That's the high energy state that has to be stabilized. That's the excited state. Things don't like to stay in the excited state, so I'm going to kick down. And I'm going to show the bond breaking. I take this pair of electrons and I put it onto the oxygen. That's the ADP leaving. And I have the phosphate at the end. Putting that phosphate onto that intermediate, why in the world did I do that? What does that afford us? What does that give us? A nice leaving group. The phosphate's a wonderful leaving group. One other way you can describe it is I've activated that molecule. And what I've really activated is this. If something attacks at the carbonyl next to it, then that phosphate can be a wonderful leaving group. Now what will attack it, if I take a look at my inventory, is here, carbon is bound to oxygen. Here, this carbonyl is bound to a nitrogen. So I've got to get my ammonia. Okay. Also, here 2 hydrogens, here 3 hydrogens. Okay. So what I'm going to do is I am going to use a base in this case. And ammonia, the lone pair is a very weak nucleophile. Okay. It can attack, but if the base takes off that proton, I now have full negative charge, which is a strong nucleophile that it can attack the electrophile. I kick up, I kick down, that pair of electrons goes off. Phosphate is the leaving group, and now you've made 2 of 20 amino acids.